Good day, guys. Welcome to another video, and today we will try to prove Bernoulli's inequality. Now, Bernoulli's inequality states that if we have any real number x such that 1 plus x is strictly positive, then the binomial 1 plus x raised to n is greater than or equal to 1 plus nx for all n element of the set of natural numbers. Now with that, let us now start our proof. Now the method of proof that we will use to prove this theorem is the mathematical induction. So let us first verify it into two first n's, right? So verification. Now for the first n, we would let n be equal to 1. Now if n is equals to 1, this will be 1 plus x all raised to 1 is greater than or equal to 1 plus 1, right, times x. Now this would be just simply 1 plus x greater than or equal to 1 plus 1 times x is just x, right? And as you can see, this is indeed true, so this is logically equivalent to 1. Okay, good. Now next, we will let n be equal to 2. Now if n is equals to 2, then this will be the square of 1 plus x being greater than or equal to 1 plus 2x, correct? Now this, we can turn this into a perfect square trinomial. So this will become 1 plus 2x plus x squared being greater than or equal to 1 plus 2x. Now, as you can see here, we have a term x squared. Now, if x is any real number, then if you square it, it is non-negative. So it's either 0 or positive, right? Now, imagine if x squared is 0, then they would just be the same, right? 1 plus 2x is greater than or equal to 1 plus 2x, that's true. And if it is positive, then 1 plus 2x plus x squared would be greater than 1 plus 2x, which satisfies the inequality greater than or equal. So this is true in both cases. So 1. Now with that, after the verification, let us now state our induction hypothesis. Now in our induction hypothesis, let us assume that if we let n be equal to k, right, you would see that 1 plus x raised to k is greater than or equal to 1 plus kx, correct? For some k element of the set of natural numbers. Okay? Now, with our assumption, let us now start our inductive step. Now, in our inductive step, we need to show that the binomial 1 plus x raised to k plus 1 should be greater than or equal to 1 plus quantity k plus 1 closed multiplied by x. Alright, so we would start at the left, and we need to show that it will be greater than or equal to 1 plus quantity k plus 1 closed multiplied by x. Alright, so let's do that. So 1 plus x all raised to k plus 1 is the same thing as 1 plus x all raised to k multiplied by quantity 1 plus x, correct? Now, from our induction hypothesis, we've assumed that the binomial 1 plus x raised to k is greater than or equal to 1 plus kx. So, by substituting that, we would find that this would be greater than or equal to 1 plus kx. Okay, so quantity 1 plus kx closed multiplied by quantity 1 plus x, right? Now, just by using simple FOIL method, we would find that this is the same thing as 1 plus x plus kx plus kx squared, right? Now, from this point, what should we do? Okay, so remember that x is a real number, right? So x is any real number. Now, if we square that, this would be non-negative, correct? Now, if this is non-negative, if we multiply both sides by k, then this will give us the following inequality, which is kx squared being greater than or equal to 0. Now, you might ask that, well, shouldn't we reverse the inequality since there might be a possibility that k can be negative? Well, remember from our assumption that k is a natural number, right? And this would just mean that k is strictly positive, right? Since there is no natural number that is negative or 0, right? It is strictly positive. So 1, 2, 3, and so on and so forth, right? So we don't need to worry about reversing the inequality here, right? Then what we're going to do is we're going to add both sides by 1 plus x plus kx, right? So plus kx squared. So this will become greater than or equal to, let's do the same thing. So 1 plus x plus kx, good. So with that, let us go back to our proof. So in our proof, we found that the binomial 1 plus x raised to k plus 1, right, is greater than or equal to 1 plus x plus kx squared, right? But we've shown here that this sum, right, this is greater than or equal to 1 plus x plus kx, right? So if we replace that, this will become greater than or equal to 1 plus x plus kx. Now that's good. So what we do now is we just simply factor out x, right? Applying the right-hand distribution. This would be the same thing as 1 plus quantity 1 plus k multiplied by x, correct? And then, by just applying commutativity inside this parenthesis, we will find that this is the same thing as 1 plus quantity k plus 1 closed multiplied by x. So, with that, we've shown that the binomial 1 plus x raised to k plus 1 is greater than or equal to 1 plus quantity k plus 1 closed multiplied by x, right? So since we've shown that, we can now then say that the binomial 1 plus x raised to n is greater than or equal to 1 plus nx for all n that is a natural number, and 1 plus x is strictly positive. Now with that, this proves our theorem, which is the Bernoulli's inequality, and we are now done.